Agro-industrial wastes as potential carriers for enzyme immobilization. Agriculture is the practice of cultivating plants and livestock. This sector is very important as it is the major source of food supply. However, agriculture sector also produces vast amount of residues every year. If these residues are released to the environment without proper disposal procedure, it may cause to environmental pollution and harmful effect on human and animal health. Therefore, the wastes produced in agriculture sector should be utilized properly. Agro-industrial wastes are the wastes produced due to the production of food. Some of the wastes or residues produced are rich in nutrient composition and bioactive compounds, and they are beneficial. As we mentioned before, agriculture sector produces vast amount of waste due to production of food. Based on the information from European Union, there are about 88 million metric tons production of agro-industrial waste in Europe in 2012. Besides, according to the United Nations Food and Agriculture Organization, it is estimated that every year, about 1.3 billion tons of food, which is one-third of global production, is wasted. Furthermore, in India, approximately 20% of fruits and vegetables production is wasted every year due to increase of production and demand. It seems like the increase of production and demand of food in the future will lead to more waste produced. Thus, we should turn the waste into useful application to reduce wastage. Agro-industrial wastes have many features with interesting potential applications such as high porosity, greater surface area, and presence of different chemical groups. These characteristics allows agro-industrial waste to become a potential carrier for enzyme immobilization. For instance, high porosity of corn wastes allows lipase to adsorb on it as a support for enzyme immobilization. In addition, agro-industrial waste is also relatively cheap so that it can reduce the cost of production. There are two types of agro-industrial wastes, which are agricultural residues and industrial residues. Agricultural residues can further divided into field residues and process residues. Field residues are residues that present in the field after the crop's harvesting. These fields consist of leaves, stalks, seed pods, and stems, whereas the process residues are residues present even after the crop is processed into alternate valuable resource. As the population increases continuously, different industries of food and beverage have increased remarkably. Therefore, huge amount of industrial waste such as orange peel and coconut oil cake produced every year. Agro-industrial waste can be divided into two categories, which are not lignocellulosic material and lignocellulosic material. All the wastes containing very low or absent cellulose such as eggshell and eggshell membrane are considered as not lignocellulosic material. Lignocellulosic material is mainly generated through the agricultural industry or by household garbage, catering, and large-scale distribution. For example, corn cob, rice straw, rice husk, and coconut fiber. According to the research that has carried out, agro-industrial wastes are beneficial if they are utilized properly. Agro-industrial wastes can be used in various fields. For example, acts as carrier for enzyme immobilization, extraction of food flavoring and preservatives, biofuel generation, and citric acid production. In this video, we will focus on the use of agro-industrial wastes as the carrier for enzyme immobilization. Enzyme immobilization is essential and beneficial because it can guarantee the enzyme recovery at the end of the process, the development of a system with multi-enzymatic reactions, higher precision for catalytic process control, and higher enzyme stability against denaturing agents and proteolysis. Let us start with not lignocellulosic materials such as eggshell membrane as the potential carrier for enzyme immobilization. The eggshell membrane, ESM, consists of two different layers, one external and one internal. The thickness of inner layer is typically 15 to 30 micrometer, while the thickness of outer layer is 50 to 70 micrometer. The composition of ESM consists of 80 to 85% of organic matrix and 15 to 20% of inorganic matrix. The organic matrix consists of 60% proteins, while the inorganic part contains a small amount of calcium, magnesium, silicon, zinc, and high amount of nitrogen. Furthermore, ESM is insoluble in water since it contains a substantial amount of cysteine and lysine, which form molecular bridges between protein molecules. In particular, eggshell membrane has excellent permeability to the substrate and to the products, makes it an ideal support system for enzymatic immobilization. ESM acts as a carrier for immobilization of enzyme such as lipase and oxalate oxidase by using covalent method. Taking lipase as an example, glutaraldehyde, which acts as an intermolecular cross-linking agent, is first directly added on ESM. Then, lipase will be immobilized to the ESM by the formation of covalent bond through the reaction between secondary aldehyde group of the ESM and the amino group of proteins. The immobilized lipase will then to be used for biodiesel production. The advantages of using ESM as carrier for enzyme immobilization includes the bioreactor showed a higher efficiency and stability. Besides, the enzymes on ESM maintain 13.5% of activity after 10 cycles of reuse. This shows that enzyme immobilization on domestic waste, such as ESM, is a very promising platform not only for developing enzymatic pads, but also for biotechnological application. Now, let us move on to lignocellulosic material as potential carrier for enzyme immobilization. In this video, we will emphasize on corn waste as an example of lignocellulosic material. Corn is an important food for many people, especially in Asia, Africa, and Latin America, and its production is one of the most important agricultural activities worldwide. In fact, during the period of 2001 to 2011, the production is increased by 44.74%. Corn wastes are generated as byproducts of corn processing, and they are in the form of corn husk, corn stover, and corn cobs. Corn wastes are porous materials even if corn husk has the highest porosity. These scrapes can be used as support for covalent and physical immobilization of lipase and trypsin. Due to the high porosity of corn wastes, enzymes such as lipase can be easily adsorbed on this kind of support. In order to promote enzymatic adsorption on the surface of corn wastes, the delignification pretreatment of corn residues with NaOH is recommended to increase the surface area. This alkaline attack is used for the enzyme immobilization of trypsin. In this case, the reduction of hemicelluloses and the lignin removal up to 67% provides high accessibility to the chemical groups and an increase in the activity recovery yield. Now, let us do a short summary about this topic. In summary, the reuse and recycle of agro-industrial wastes is the main objective to be strongly taken into all the world in order to safeguard the environment and utilize them in value-added applications. Besides, agro-industrial wastes are promising support for enzymatic immobilization due to their easy availability, biocompatibility, and inexpensiveness. Furthermore, in the future, immobilized enzymes are going to play a vital role in various industries including pharmaceuticals, chemicals, food and fuel industry.